All right.
Hi, Professor.
Hi there.
Can you hear me?
Okay. So,
Hello. Can you hear me?
yes, I can.
Oh, okay. Hi. So I had some lab due, like I did to demo. When would be the best time to demo?
Most
Have like,
like most likely Wednesday, as I've mentioned. I won't have time before Wednesday.
okay. So Wednesday in person or virtual?
Virtual.
Virtual. Okay. Do I need an appointment or anything?
No, no,
No. Okay.
we just email. We'll
Email.
just do
Okay.
something over email.
Oh yeah, I did email you about
Yep,
this.
I just haven't had the chance to respond. I've been busy.
Uh, okay, perfect. Thank you.
All right, we left off at this problem. This problem we'll come back to at the end if we need to, but it's fairly boring, so I'm not going to touch it. Which says here's a recursive method for searching for a key. I'm not going to bother doing that one because it asks us to rewrite it using iteration, which is you just use a stack or you don't because it's a tree and you don't have to backtrack anywhere. So it's fairly straightforward on how to solve that one, just using a while loop and an if else statement. This one was much more intriguing. And again, it's one that we've done in the final exam before. Write a Java method named mir that takes a reference to the root node of a binary tree. It creates a new tree with its own nodes. So it'd be useful for them to specify that kind of stuff. That's the mirror image of the original tree. For example, if root is a reference to the tree on the left, then we would create a completely new tree and it would look like what's on the right. Make sense? So you've got 1, and then you've got 2, 3, and then you've got 3, 2. And under 2, you had 4, 5, and those nodes are still under 2, but now they're 5, 4. So it's a complete mirror image. Everything that's been so every node has its children swapped, essentially, right? All right, so let's go ahead and create ourselves a we'll create ourselves a node public static class node. Actually, it should be private. And that will have a construct, and basically we'll just simply have a private node. Let's see. Yeah, let's call it node of E, node E left, private node E. Yeah, this is just simply the node class we've been working with before, node E right, and private E item, public node E item. And what we're going to do now is we're going to say this dot item is equal to item, so that we have an initializer. You could make more constructors if you wanted that took in the left and right, but I'm not going to bother because there's just no need. Exit. Okay, so now what we do is we take public static mirror and it's going to take in a E, public static E, and there we go. So how do we do this? So first off, I'm going to return null to quash the error because I never like having my, we'll remove that at the end, but I hate having the compiler yell at me at any point. That's just me. So I do whatever I can to make sure that the compiler never has an issue with what I've written. Now, let's go ahead and go through a base case. So what is a base case for mirroring a node? The root is null, right? If the root is equal to null, we know how to create the mirror image of that. The mirror image of null is just null, right? So boom. We've got to remember to return it, of course. Now, what else do we need? So now that if it's not null, we can assume that it's ourselves. And sorry, if it's not null, and we've been passed something like 2, okay? Right, because this is the root of a tree or a subtree. Then this 2 here and this 2 here are they're different nodes. In other words, they're different, they're different 2s. So they're clones of each other, right? New tree with its own nodes. So we have to make a new node. So let's go ahead and make a node E mirror node. So we can actually hit the O key. Mirror node is equal to new node. And it's going to be root dot item. It's going to take in the item from the root, and we're going to make our own node, right? And now that we've got that, it makes sense that if we've created a mirror of a, if we've passed in the root of a node, sorry, the root of a tree or subtree, we create we return the new root of that tree mirrored. Okay. Now, with regards to how we should handle like 2 being a left child and 2 being a right child, that's not my problem. From 2's perspective, he's the right. We don't have a parent pointer, and we didn't get any information, so that's not 2's problem. 2's problem is to figure out what to do with its children, right? And if it figures out what it can do with its children, then 2's parent can figure out what it wants to do with 2 and swapping its children around. So what we need to do is that we need to swap my children. So right. So what we need to do is now on the first glance, you might think, okay, what I need to do is I've got to say mirror node dot left is equal to something. Let's say it's equal to new node root dot right. And right, so this creates a new node based off the right node's item, right? This is wrong, but I'm typing it anyway. Okay, so don't worry about getting this. Get the left side and the right side, the left side of the equations. But other than that, all right. And you're thinking, okay, so left, I'll swap with my left item. I'll create a new node that has my left item in it, and I create a new node that has my right item in it, and swap them around, right, in the appropriate places. Make sense? However, that's just going to basically, if I pass them 1, that's just going to create 3 and 2, and we're not going to move anywhere from there. So instead, what we need to do is as they say, much easier if we write recursion. We notice that, wait a second, okay. So what I'm going to do is I'm going to pass in, is that if I'm passed in 2, then what 2 should do is that it should create a mirror of 4 and a mirror of the subtree that starts with 5. Creating a mirror of 4, not too much. It just simply creates a new node for itself. A mirror of what's on 5, though, right? 5 will, we can see that 5 swapped its children. So what we do instead is remove these items and instead type in mirror and mirror. So what mirror does is that, let's see, why is it giving me a warning? Main unchecked assignment. Oh, right, because returns no D. There we go. So mirror, what it does is that it creates a mirror of the right side, attaches it to the left side, and takes a mirror of the left side and attaches it to the right side. Again, it doesn't look like it should work, but because it looks like it's just pseudocode, but it does, because what we do is that mirror creates a new node for each of those and tells its children to swap, and for each node it tells its children to swap each other. Although, let's see, root dot left. So from there, and yeah, the only thing you might be like passing in, wait, am I passing in a mirror node at any point to this? No, you're not passing in any mirror nodes here, left and right. These are all from the original, all the root calls are from the original tree. So that solves that problem. What's the big O time for the implementation of that method? Well, we for each node, we duplicate it and tell it to duplicate its children. So each node essentially gets touched once without backtracking, right? We visit each node once, we handle it once, does not backtrack, and then we're done. So it's O of n, because every node basically gets visited a linear number of times. Or every node has a linear number of operations, I should say. There's some supplemental problems over here. Let's see. If a binary search tree is not allowed to have duplicates, there's more than one way to delete a node that has two children. One way involves choosing replacement from the left subtree. If this is done, which node are we looking for? The largest node in the left subtree. Yep, the largest node in the subtree, it's A. We always look for the rightmost node, which is the largest node in the subtree if we're using the left subtree. Okay. Which of these would be for key value pair stored on disk? On disk, I think that's B tree, but that's because B trees are kind of designed for that. Let's see. So let's see. Let's take a look at the following recursive method. Oh joy, that is an annoying one. So what is called returned by the call 7 and 2? Int 7, int 2. All right. So for this one, we keep going until I guess A is less than, until A is divisible by B. So let's see. Now there's no branching, so this actually makes it fairly straightforward, if annoying. So we're given 7 and 2. Okay. Is A 7 mod 2 equal to 2? No, it is not. Otherwise, do A plus B, A minus B. A plus B, A minus B. Right? A plus B, A plus B, A minus B. Okay, and then we do the same thing. Is 9 mod, this gives us, A mod B gives us 4, which is not 2. So we do 14, and then 9 minus 5 is 4. I swear I passed like 5th grade math at some point, you know? Okay. Got like 4 hours of sleep last night. My kid's sick, so just a bit of issues in the fatigue area. So 14 mod 4 gives us 2, right? 14 mod 4 gives us 14 mod 4 gives us, so that's 4, 8, 12, so that gives us remainder 2, so we return A at that point. So there you go. So that's that one. Which of the following sorting algorithms does not require O of n squared steps in the worst case? Okay. Insertion sort, worst case scenario, that's O of n squared, right? Selection sort is always O of n squared. Best case, average case, worst case, it is O of n squared no matter what. Okay. Heap sort, O of n time to build the heap, n log n to sort that heap, or to turn that heap into a sorted array. So that's n log n time, right? Bubble sort is classic O of n squared, worst case scenario. Quick sort is the one that's meant to trick you, because we often refer to quicksort as an n log n algorithm, and we kind of classified it. But in worst case scenario, quicksort is an O of n squared algorithm. It's just that O of n squared happens very rarely. You kind of need to have it for quicksort to be O of n squared. Basically, you have to select your pivot poorly every single time. Which can happen if you've got like a reversed list and you're not like doing any kind of optimization for what you're trying to sort. So quicksort. So this one does not require O of n squared steps in the worst case. That one. So with this one, let's see. Is there anything else in here that was worth mentioning? That one I said I'd come back to if I wanted to, but I have other things to do. We've done this one. Now let's go on to this one. I love this one. Which is, we've got, let's see, we don't need a priority queue, implement a priority queue. So in this course, we've seen many different data structures, including the following: lists, which are linked lists or array lists, 2D arrays, stacks, queues, hash tables, trees, binary search trees, undirected graphs, directed graphs, and directed acyclic graphs, or DAGs as we call them. All right, for each of the following applications, indicate which data structure would be most suitable and give a brief justification for your choice. For data structures like trees and graphs, describe what information is stored in the vertices and edges, and if the edges are weighted, describe what would be stored in the weights. Okay, so the map of the Puget Sound highway system used to display traffic times on a web page. The map displays principal cities, intersections, and major landmarks, the roads that connect them, and travel times between these roads. Travel times along the same road may be different in different directions. Yes.
Directed graph.
Yeah, this is a directed graph. This is a totally directed graph. So what are the vertices in this case? Remember, it's all about relationships. So what are we care? What are the relationships, and what are we care? And what are things that have them? Yes. Yes. Yeah, places you want to go, places we want to travel to. Those are our nodes, and our edges are how we get to them, and the weights are how long it takes. Okay. This is kind of old classic before Facebook came along and Twitter and all the other social networks, because now those are basically the big graph problems. Chessboard, 8x8 board used for a game of chess. I wonder if this is a bit familiar. Each square on the board is either empty or contains a chess piece. What's a good data structure we've used for this one? What did you use for this one in your homework? Don't be shy. This one's not a trick question. Yes, it's just an array. I heard you whispering it. It's just an array. It's a 2D array. Technically, that's a data structure. All right, a computer model showing the dependencies between steps needed to assemble a B-787 airplane at Boeing's Everett plant. Let's go. So computer model showing dependencies between steps. So which of these data structures is best for showing the dependencies between steps? Anyone? My gosh, I can't hear anybody over you all talking all at once. It is a directed acyclic graph in this case. It is a graph because what we're trying to do, we can embed this as a graph because you basically say, okay, here's the steps and here's the next steps. But what's important for directed acyclic graphs is that, or dependencies, is that you never kind of have dependencies that are circular like this, right? In order to do A, you have to do B. But sorry, in order to do C, you have to do B. In order to do B, you have to do A. In order to do A, though, you have to do C. That's a circular dependency. You'd never have that. So it would be directed acyclic graph. Yes. A tree would be close because trees are technically directed acyclic graphs, but because trees can't do this. Or they can't do this. That's why. A tree is close though. All right, a list of legal words in a Scrabble game. We want to quickly check whether words used by players do in fact exist in the list. And don't be led astray by the fact that it's using list there. Yes. Tree would get us that, but what could be even quicker than a tree for checking if something exists? Yes. Yeah, hash table. Because a tree, we could do it in log n time to check if it's tree, with tree set. Hash set would get us in constant time to check. Description between inheritance relationships between classes and interfaces in a Java program. So that's a bit interesting because here's the thing. In Java, well, technically I would say it's kind of a tree. I'd argue either a tree or graph because here you could, everything starts with the object. Everything's an object in Java. And if it was classes, that would be the end of it. Okay. But with trees, you have one parent. And with a class in Java, you can extend one class, okay? But you can implement as many interfaces as you want, right? So with that, I'd say it has to be a graph at that point. Just a weird, messy graph where what we're looking at is what's a parent of what, essentially, in the graph. A history list recording sites visited by the user in web browser. As new sites are visited, they're added to the list. It supports the operation of going back to the list that was visited before the previous page and going forward to the next list page visited. In other words, the back and forward button. What are we going to use? So this one's ambiguous, but that's why the justification exists. I could argue that the back button and the forward button exist independently as stacks. You could also argue that the back and forward button are just simply interfaces to interact with a linked list. So either way, either of those answers work. All right. So let's go to this next one. In your solution, perform a breadth-first traversal of a binary search tree and print out the node data values in the order they are reached during the search. So this is breadth-first search for a binary tree, and that's actually rather trivial to do. Mainly because with breadth first search in a graph, you have to like keep track of where you've been and you need a queue. For breadth first search with a tree, let's see. We just need public void BFS. I think we may just need a queue with that. BFS node E root right, gotta make it static, make it callable, and put the E in the right place. Take it out of the wrong place. Okay. Now let's do this. Q, remember, Q is equal to Q of node of E. Q is equal to a new. Can I do Qs? Oh, cool. In case you're just wondering what happened there. Cool feature in Java. So Q is an interface. So I can't make, remember, you can't implement an interface. You cannot create a new interface, right? If it was just this, it would error like crazy. But what you can do is you can create an inline class definition, an inline implementation of an interface. That's what that did there. Obviously, that's not a great idea to do on an exam or in general, to just completely implement the Q interface, but it's an option. Instead, we'll just simply use a linked list as the implementation of our Q. Root, and then we'll say Q dot, and then offer or in Q or whatever the term you want to use for it. In Java, it's offer, but if you're doing pseudocode, NQ, DQ, I don't think anybody's going to care. So offer node E. We're going to offer root. Well, the Q dot. Okay, actually, we're going to say if. We're going to make this idiot proof. If root not equal to null, there we go. So if root is null, we're just going to skip it and not do anything. So long as root is not null, well, Q dot is empty. There we go. While Q is not empty, we need to just simply, what we do is that we say node E current is equal to Q dot poll to get it off, or DQ or whatever. So while it's not empty, we get the current, and we say, and we'll simply system. It wants us to print out everything as we get to it, so we'll say system.print. We'll go ahead and print it as opposed to print line it. We'll print current.item. We'll just print line, whatever. It doesn't matter. I'm not going to overthink this. So we get to the item, we print it out, and then we need to add its children in. Q dot, to do breadth first search, we're going to go across the left children. So we're going to do Q dot offer current dot left. And then, would you believe it? The next thing to do is add current dot right. Now, normally what we'd be having to do in a graph is I'd have to be double checking, hey, are these nodes I've seen before, but we're in a tree. Children have only one parent in this tree, so there's no chance we've seen these nodes before we add them to the queue. So the only thing we'll want to do besides this is maybe instead of that, we'll go ahead and just simply do if, yeah, we'll allow, I'm going to be even lazier. Okay, give me a second. I'm going to redo this to make sure that we have good ending conditions and be super lazy about it. All right, so we're going to add that item. So we're going to add the child to the node to the queue no matter what. So if root is null, I'm going to add it, but I've got this thing to catch it if it's null. Okay. Similarly, I'm always going to add the children even if they're null, but if I find that the current thing I'm on is null, I'm just going to essentially skip it. Make sense? That's the main concern for this, which is handling those null values. But the other way you could do it is, not add it to the queue if it's null. I just had enough time while I was coding this up to think about the best way to do it. All right. Here's an adjacency list representation of a directed graph where there are no weights assigned to the edges. Draw a picture of the graph that has the above adjacency list representation. Okay, adjacency lists, right? They look like this. They say, hey, here's our nodes. Here's a node, and here's the list of all the nodes that I'm connected to. Okay. So let's go ahead and draw a picture of this. We have A, B, C, and D as our nodes. This appears to be a directed graph since A goes to D, but D goes to nothing. Yes, says directed graph. So, okay. Reading the question explains the question. B, so A goes to B, it goes to C, and it goes to D. Right? It's not saying you go from A to B to C to D. That just means this is a list of all the things. So A, B, and D. B goes to A. C goes to B. And D doesn't go anywhere, and it's also planar, meaning that I was able to draw it without any of the edges overlapping, other than this due to my bad drawing. But you could draw it without anything overlapping. All right. So now we're going to go back. Another way to represent a graph is an adjacency matrix. Draw the adjacency matrix for this graph. So we're going to go ahead and do that too. Adjacency matrix looks like this: A, B, C, D, A, B, C, D. We'll leave it blank if there's no edge. And otherwise, we will not rely on my pathetic, my pathetic drawing of straight lines, but instead use lines that are straight, although not parallel. Thank you. So there we go. And let's go ahead and add one more over here. So there's our matrix. So A goes to, so we don't have anything. I'll just put a dash in to check it off. So A goes to B, C, and D. B goes to A. C goes to B and D. And D goes to nothing. that was what an adjacency matrix would look like, although you probably would be better off either leaving those blanks or writing zeros in here for if there's no edge. Because that's always a philosophical thing, because if you're working with weighted, if this works for directed unweighted, but if you've got weights, then suddenly ones and zeros doesn't work, because the zero would imply there's a no cost weight. So if there's a, so that's why often you'll leave it in representations. You'll see it left blank if there's no path, or you'll see the entry as null or as infinity, because in paths, infinite cost is a good way to say there's no edge. It will just take you forever to get there. This is a good graph for Dijkstra. I know this one I've done a number of times for Dijkstra. Okay, considering the following directed graph, we're going to do Dijkstra's from node 1 to each. So this is just a bit of a pedagogical nitpick on my point. Okay, this is bad. This is a bad question. So it's a good question, but the presentation's bad, because the node should never be named numbers if you're using numbers for the edges. 1 has a weight of 5, 5 has a weight of, that just doesn't, you're introducing information clutter. So that's why I always like to use symbols for those. So that's what we'll do to make sure that it's that we don't have any issues here. So what we're going to do is that we are going to zoom out. Sorry, we're going to zoom in a bit, and we are going to, instead, we're going to do A, B, C, D, E, F, draw. No, that's highlighted. That's not what I want. I thought I could be clever by getting the size of that to be. No, there we go. Now I'm being clever. Okay. So for Dijkstra's, the important thing to keep track of is okay. That's all I need, which is the node A, B, C, D, E, F, then the distance and the predecessor, how we got there. So we start out with the distances to everything being infinity, except for the nodes that are directly connected to A. A starts out with a distance of 0, and its predecessor is either itself or nothing, depending on your preference. Okay, predecessor itself, you get to A from being in A. Okay, so now we can also say that since we're connected to B and D, we can initialize those with 2 and 3 respectively. A is done by virtue of being the node that we're starting with. So now what we go through is we look through the list of distances and select the best node of the one that we haven't visited yet. So 2, infinity, 2, 3, infinity, infinity. So 2 is the cheapest. So we're going to now start looking from D's for D's information. So, from B's information. B, the cost to get to B is 2, and B has 2 new edges that we've introduced. We have, that get us to E and C. So let's go alphabetically. B to C, the cost to get from B to C isn't 5, it's 5 plus the cost it was to get to B. So the cost to get from B to C is 5, but that's not what we're writing down in the distance table. What we're writing down is the distance it takes to get from A to each of these things. The distance to get from from A to C is the cost it gets to get to B, which is, we already know it's the shortest thing because we've determined that already, plus 5. So the cost to get to C currently is, I forgot to write these down. Everybody starts with the precedent. The cost to get to C is 7 going through B. Okay, then B to E costs 5 for similar reasons. Because 5 is less than infinity. Imagine that, right? Okay, so now we've got 7, 5, 3, and infinity. So we'll look at D next. D, the cost to get from D to C is 1. And so the total cost to get from A to C through D is 4. 4 is less than 7. So this is why I like this one, because it does actually have one where you have to update here, right? The path to get to D, to get to C through D is cheaper than what we had earlier. So we'll say D and 4. Make sense? That's the Kiefer-Dijkstra's algorithm. You always make sure that you update the cost to the lowest path. And that lowest path is the cost it gets to get to where you currently are looking at, plus the cost to get to, so the cost to get to C is, again, the cost to get from D to get to D in the first place, as well as the cost to get to D from D. Okay, so we're done with that one because D only had one edge. So now we have C, E, we have C, E, and F, which are 4, 5, and infinity. So next we go to C. C has a single cost. So it is C. The cost to get to C is 4 plus 2, that's 6 to get to F. 6 is less than infinity. So C and 6. Now E, the cost to get to E is 5 through B. To get to F through E would be 9, which is more than what we have for F. So we're done there. And here's so when you check it, now the nice thing about Dijkstra's is that it's easy to check your work. So let's go ahead and actually use this highlighter now, because you can go and say, okay, to get to B, we went through A. To get to C, we went through D. To go to D, we went through A. To go to E, we went through B. And to go to F, we went through C. So essentially, we leave out all the edges that would be that would be unoptimal for us to take. Again, this is going through A, you know. So you don't always end up with a directed acyclic graph like this. But the point being is that you're just graphing out the edges that you want to get for the shortest path. And it's always the shortest path. To find out the shortest path from A to somewhere else basically requires us to go and figure out the shortest path in general from A to every other node. Okay. And there's some questions about, like, what is the cloud of known vertices? List the order in which nodes are known. We could have listed, like, okay, this is the first node, the second node, the third node. I mean, that's not too hard. We can do that post after the fact, where the nodes we wanted to go to were 1, and then we went to B, 2, 3, and then we did C, and then we did 4, 5, and then 6. It's not too scary there. Okay, that's graphing problem. That's Dijkstra's. Okay. Okay. So V is the number of edges in a directed graph, and E is the number of edges. What is the running time of Dijkstra's in big O notation? Give a brief description of your answer. So, well, what we need to do is that we need to go and for every node, we check every edge. So is it not V plus the number of E? Well, let's go ahead and check Wikipedia, because actually this has a number of interesting questions. Okay. The original Dijkstra's algorithm was actually less efficient than what we've got now. The answer is the real runtime for Dijkstra's is based off of what kind of heap you're using. Because one thing you do, because yes, there's the number of edges and the number of nodes, but what you have to do is for each node, you want to examine the number of edges, right? Keep in mind, so first off, we need to process each node. So first off, we got to examine every single edge once, okay? The maximum number of it, or ideally we should be examining every edge once. That's a round edge, so that would be vertices squared is kind of the maximum runtime, maybe. But the big thing is that when we were going in through this chart and picking which one to go through next, I was kind of going linear fashion, figuring out which the biggest one was. So for every node, I was also going through and checking each vertice and seeing which one had the shortest path. So I did that for 6, then for 5, then for 4, then for 3, then for 2, then for 1 squared. So that's an upper bound on our runtime. Okay, just kind of doing this as unoptimally as possible. We have to go to, we've got basically V squared plus E, which is worst case that number. But if we look over here, worst case performance, it says is edge times V log V, number of edges plus V log V. Okay. And the reason for this is that it says, let's see, running time. Yeah, the upper bound can be simplified to E, because it can be simplified because E is O of V squared for any graph. Hey, see what I just said there? But that simplification just disregards the fact in some problems, the upper bounds for E may hold. In other words, it may be a sparse graph, right? As opposed to a dense graph. And the idea here is the simplest version. What we do is that we went through, we had the number of, we had to examine every edge once. And then for every vertex, we had to look at what vertex we want to do next. So V squared. Now, choosing the next vertex is the expensive cost. Okay. So in graphs with far fewer than V squared edges, Dijkstra's algorithm can be implemented more efficiently by storing the graph in the form of adjacency lists and using a self-bouncing binary search tree, a binary heap, a pairing heap, or a Fibonacci heap as the priority queue for extracting what's the next thing to look at. Because what the next node is, that's kind of a min-heap problem, right? That's a priority queue. Figure out, it should keep track of what it is. But to get it really optimal, we have to use this thing called a Fibonacci heap, which, if I recall correctly, in the art of computer programming, CalCP, which is Knuth's kind of, it's not the Bible, it's more the Vatican archives because nobody really reads it, you know. I believe he leaves it as an exercise to implement it. It is a implementation of the operation. It is a very interesting heap. Where basically oftentimes we can get constant time operations for the heap. So it's kind of on average. Worst case, just leaves it blank here. And again, this is not an old article. This is around as old as I am. I'm sorry, not a recent one. It's around as old as I am. So fairly old at this point. All right. So anyway, it is O of V. What is the runtime? It is V plus E, the way we were implementing it. Okay. two of the most common divide and conquer sorting algorithms are quicksort and merge sort. In practice, quicksort is often used for storing data in main storage rather than merge sort. Give a reason why quicksort is likely to be the preferred sorting algorithm for this application. We never really talk about that. Main storage in this case means RAM as opposed to disk. Now, I can tell you why merge sort would be rather used for disk. It's because you can merge, because you can take that, work on it, save it, and work on another chunk. Whereas quicksort all is kind of all done in place, is kind of the idea. And that's the main thing. Quicksort can be done in place, whereas merge sort is, if you remember, memory inefficient. It is a memory cost. There, unless you're using linked lists, doing an in-place merge sort is we don't do that. Quicksort, on the other hand, very easy to, we've seen an easy way to do the partition algorithm in place. So the recursion is the only thing that takes up memory, which isn't that expensive in comparison. Okay, this is a great question though. Quicksort's worst case runtime is O of n squared, but the expected running time of n log n in the partition function works well. What needs to be true about the partition function in order for us to have a n log n? And in practice, how can we ensure this happens? So what has to be true about the partition function to guarantee n log n is that the we need to choose that the pivot should always be a value that's close to the median of the list. The median meaning the, not the average, but like kind of the middle value. Okay, so in practice, how do we ensure this happens? Well, we saw one way this happened in the textbook, which is that we select some constant number of items evenly spread throughout the list or the subsection of list that we're sorting, and grab the median of that constant sample. And that's a median of a random sample, but it's better than nothing, than just going blindly for it. It helps, is the idea. Okay. So all the negative integers precede 0. Okay. Sorting algorithm. We're not really going to go over that right now because we have 25 minutes left and I want to get to some other things. Let's see. So this is a good one for practice, which is the Eulerian path. This is kind of where the entire idea of an Eulerian path comes from. If you missed the video on that, which is the bridge of Königsberg problem, which is it possible to walk through the town of Königsberg, crossing all bridges in the town once and only once? Right? That's what an Eulerian path is. And you'll find that there is no way to basically start at one of these 4 islands, one over here, then you've got the middle island, and you've got the island over here, and then you've got this other side of the river over here, right? There's no way for us to go and hit all the bridges and all the surfaces and all the islands just once, right? A crucial fact, a graph contains an Eulerian path that consists of one connected component, meaning all the vertices can be reached from any other vertice, and it contains no more than 2 vertices of odd degree. So you should so this is good if you want to get practice working with graphs, if you want to create an algorithm for it, but we're not doing really that kind of stuff in our final exam, so I'm going to skip it. But it's a good puzzle for that. Instead, I'm going to go ahead and talk about a problem that we no longer have on our because the final that was attached to it's no longer extant. So I'm going to go ahead and use the problem from it because we need to practice on doing hash maps here. Okay. Okay. So suppose I have some kind of, so here, let's go ahead and work on a hash map practice problem. Suppose I have a log file. Username, and the log file is basically is composed of the following elements. Username space login time. Username space login time and whatever time units. Let's go ahead and say seconds. Username space login time. It doesn't matter what these login times are. I'm just putting in numbers to kind of see. But notice that this is a cumulative login time for each user. This is essentially what we're looking at here is Al's logged in for 78 seconds. Bob logged in for 213 seconds. Alice logged in for 428 seconds. So this is the duration of different sessions that a user logged into a server for. Make sense? Okay. So what's going to be the problem I make us do? For each user, find the average time that they were logged in for. For every user, I want you to find out what the average amount of time they were logged in for. So this one's actually a nice one because it's long and much longer than I would do on the final because it requires us to do this. Public static void average session. And I'll give you what they gave the students initially, which is simply string file name. Because I wasn't going to make it easy for you. And then let's go ahead and map string to integer. Equals new hash map string to integer we'll call them login account and login time. And we need two of these maps. Why? Because we're counting for an average, we need to count two different things. And this was provided, by the way. Which is you need to count how long the student was logged in for, the total time that this user was logged in for, but you also need to count how many times they were logged in for so you can get the average. And we need to use maps because trying to do this any other way will be torturous. Okay. So what first thing we need to do is we need to go ahead and scanner is equal to new scanner, new file name, enter, import class, and then it wants and then it will want me to do like a try catch statement or something, and we'll just simply say throws exception to just make it be quiet because I'm never going to run this anyway. And that gets rid of the need for a try catch. The exception means it's somebody else's problem. So we've got the scanner, and while scanner dot has next line, because I want to read these lines one at a time. String line is equal to scanner dot next line. So while we're going, so now that we've got so we're going to read through this. There's a file reading one at a time. Now, as we read the file, let's go ahead and build up these maps. So line dot split. By default, it should, let's see, does it do a split by default? Nope, we want to split on space. And then what we'll do is, as we're splitting on spaces, we will say, I'll call it string. I always like to do this if I'm splitting it up into parts. I'll just simply call it parts. String user is equal to parts 0 and int session int how long was their login length? It will be integer dot parse int parts 1. Right, so much easier in Python. You just simply say int. So there we go. We've split it up into the appropriate parts. And now we can, and now I'm going to go ahead and be very brief about this. Actually, I can be verbose. Go ahead. So let's go with the standard way this works. If login count dot contains key user, right? If we have seen this user before, else if we haven't seen this user before. So if we have not seen this user before, let's do login count dot put user. We've seen him once. And then login time dot put user and the value here, which would be length, right? Otherwise, if I've seen them before, put login count dot get user plus 1. Login time dot get user. So if I've seen them, if I've seen him, this user before, update their time. Otherwise, don't. Okay. Otherwise, I've got to create their time to begin with. Now we're done reading the file. Now we just need to calculate the average for this, which is not too bad. For string user in either dictionary works, login count dot key set. We can iterate through that. So for all the users, what we're going to do is we are going to system dot the print line. And this is going to be a long line, but whatever. Actually, let's go ahead and say double average is equal to login count dot get login count dot get user, that's the number of times, divide login time dot get user, and we've got and we do division over here, and then I'm going to convert it into a double by, and the way I'm going to make sure that this, that I do, as I stop doing integer division, as I just convert them I convert the amount of time they've been in there to a double, so that now when we're doing this time divided by the number of counts, we actually get a double out of it. And average. And there we go. We're done with this one. Okay. Now for the last one, last couple of problems from here. consider insertion sort and merge sort. So this one has a lot more theoretical problems as opposed to programming problems, but I know that for some of you, those are scary. So consider insertion sort and merge sort. For each algorithm, what will be the worst case asymptotic upper bound for each runtime? If you know, additionally, the input's already sorted, it's reversely sorted, and it's n copies of the same number. For each case in sorting algorithm, state your answer and justify it in one sentence. So let's go through insertion sort, okay? And then we'll go through merge sort. Actually, let's go merge sorts first because that's easy. Merge sort doesn't care. For all the answers, merge sort's worst case is O of n log n because merge sort performs the exact same way no matter how everything is sorted. Does not matter. The only thing that might change is the number of swaps, but again, depending on how you implement that, that's not really going to be too much of a deal. And besides, we don't care about swaps. We care about comparisons for the asymptotic upper bound. Merge sort always is n log n. No better, no worse. Now for insertion sort, this changes. The worst case scenario for merge sort is, if it's already sorted, is the best case scenario, which is that insertion sort doesn't take any time to sort at all. It just simply goes through. It's already sorted, great, don't need to move anything. Insertion sort, it would be O of n. If it's reversely sorted, insertion sort, that's O of n squared. That's the worst case scenario for insertion sort, with everything being sorted. Because what we'd have to do is that we'd have to go, okay, 9, and then swap not. If we had 9, 8, 7, 6, we'd have to go and swap. We'd have to go 8, 9, 8, 7, 6, 7, 9, sorry, 7, 8, 9, 6, and then 6, 7, 8, 9, and then 5, 6, 7, 8, 9, and so on and so forth. It would get we'd have to move the maximum number of items. The input is a list containing n copies of the same item. That's just being sorted with extra steps, right? If the exact same copy of the same number, it's sorted, right? Because we're assuming, of course, the numbers here are fungible, which they are, meaning that like if you had a list of 5s, no one 5 is better than any other 5, so it doesn't matter which one is which. Okay, so again, O of n. All right, so let's see. Okay, so let me go ahead and let's see. So let's go look at this one. Suppose we have a hash table in it, and I've considered doing one like this in my final exam before, but I worried that it would take too long because it requires some issues, or sorry, requires some thinking that you'll get to. I just worry about the amount of time it takes to get to it. Suppose we have a hash table and inserted some of the elements. When you inspect it, you realize the result looks as the picture below. Being a good student, you realize there's a problem. What is the problem here? Give an example of the hash function and what would be a better hash function. So here's our table. Now, first off, this is using collision resolution. Well, sorry, the collision resolution strategy being used here is buckets or chaining. In other words, each slot doesn't hold one item, it holds a linked list of multiple items. So what's the issue here? What's going on? What's our issue? Anyone? It's not a trick question here. What's the issue? We've got too many what? Yes. Yeah, we've got too many spaces. We've got too much unused space. It's not evenly distributed. Right? We want these linked lists. We want, no matter what the strategy, we want everything to be evenly distributed in a hash table as best as we can. Okay? And we don't have a lot of empty spaces here. So, okay. Now the next question. What is a hash function that could have given rise to this? All right, let's take a look. This may help if you read it out loud. So let me read it out loud. Index 0 holds 0 and 30. Index 2 holds 21, 31, and 1. Index 4 holds 2, index 6 holds 33 and 63, index 10 holds 15, index 12 holds 26 and 6, index 16 holds 38 and 8. So there's a pattern here, right? What's kind of good pattern going on? I don't need a hash function. What's the pattern? Like, what's common with all the numbers that end up chained together? So what's common between 33 and 63? What's common between 26 and 6? What's common between 38 and 8? Yes. Skipping ahead there. What's common between them?
Well, they all have the same like mod, so it's mod 6 for 38 and 8 for 16.
They all end with the same digit, same one's place. That's but yes. So now we can get there, as you were saying, by doing a modular function. And what we could say is that we can say that h of x is equal to, and then what we could do is we could say, first off, it's basing it all off the last digit. So x mod 10, which would get a 0, 1, 2, 3, 4, but now it disperses them a bit more. So x mod 10 times 2 gets you into those. Any other math equation that fulfills where all those numbers would go is perfectly fine. We see that 0 ends up in 0, but we can see over here that 33 and 63, right, those guys, they end up in index 6 because 33 mod 10 is 3 times 2 is 6, so it ends up in index 6. Same for 63. So not a good function there. What is a better hash function? Pretty much anything else that would give it at least a chance of landing into a space. It's got 20 spaces, and so even though 20 would technically be better, even though you know that's not great. For reasons for mathematical reasons covered in the textbook and in other textbooks, really what you want to do is actually kind of mod it by a nice prime number. That helps distribute things a bit better because you don't have any common divisors or common factors, I believe. No, I haven't looked at the reasoning behind it in like a couple years, so I forget. But the point being is that modding it by anything else that will allow you to use any of those spaces would be a good idea. All right, 5 more minutes. Let's see. All right. Suppose we first insert an element into X into a binary search tree problem that does not already contain X. Suppose we then immediately delete X from the tree. Will the new tree be identical to the original one? If yes, give no more than 3 sentences. If no, give a counterexample. Draw pictures if necessary. Anyway, so I like this one because it's actually open-ended and you can argue your way into success for either. And then you can completely argue out of this by going all ship of Theseus on me, which is that you know, if we change it out piece by piece, is it really going to be the same thing? But that's philosophy. But regardless, so first off, if we make the answer is it depends on what assumption you're making. If we are saying it's a binary search tree with that we've learned in class with no self-balancing capabilities, then yes, then it will be identical. Okay. If it self-balances though, if this is a self-balancing binary search tree, then when you add an item, it's possible that the tree restructures itself, you know, to rebalance the tree. And then if you remove that item, well, that could rebalance it again, and then you might end up with a completely different structure. On the other hand, if we're not dealing with that and we're just dealing with the assumption that we're adding it. Okay, if we're just the fact that we're adding a node. Right, here's a root. Each of those has a subtree, and when we add an item to a binary search tree, it always ends up as a leaf. So it could be here. It could be here. You know, it's going to end up as a leaf as one of the subtrees. Okay. That's where it's going to, and I mean, that's where it starts in the self-balancing process before it starts doing rotations to handle that. But here, but in a non-rotating tree, this is where we would end. This is where it would be. And then to delete it, well, deleting a leaf is very simple. You just delete the leaf and replace it and tell the parent to replace it with null. So it started as, so it starts as null. You add a node into that spot, and then you replace that the item with null again. The tree structure doesn't change. So if you add it, immediately delete it, no, it doesn't change. Okay. All right. Suppose we have, last question. Suppose we have a heap and two values, v1 and v2, such that all values are distinct. Let heap 1, 2 be what you get if you put v1 and then v2 into it, and then h21 if you put in v2 and then v1. Give an example of the heap, the starting heap, then v1 and v2 such that those two are not equal. This is the point being that, so okay, so let's see, 5, so min heap, let's go ahead and do 5, 7, 8, 5, let's see. And then what I need to do is I need to do, let's see, 10, 11, and let's go with, okay, yeah. So this is going to be my starting heap. And then the numbers I'm going to add are 1 and 2. Let's see what happens. So if I add 1, I get 7 down here and 5 over here, and then I get 1 over here. So I would end up, so if I add in 1, I would get 1, 5, 7. So now we need to start with the same heap again, which was, I said, 10, and then I need to add, oh, and then if I add 2, right, I have to add 1, and then I have to add 2. And then I would end up with 2 and 8. And now if I go ahead and do 2 and then 1, so let's go ahead and add 2 over there. 2 swaps with 7, then swaps with 5. 2, 5, 7, and I believe if I add 1 over here, instead what we're going to get is, oh, no, I messed up. 1, 2, 8. I've done this one before. It's just a matter of coming up with the right numbers, so that it. Wait a second. Okay, even easier. 5, so this is 5, 7, 8. Five, 7, 8, 10. Yeah, no, this is easy. 10 to the 10th, 10 to the 100th, right? 10 to the 100th, 10 to the 10th. Doesn't matter, just really big numbers on the bottom. And they just, they won't restructure because they're all the way at the bottom. Or, you know, better yet, 8, 11, and 12 versus
12, and 11. All right. So we are at time or past time. So I just want to say, this is always my